Hi linear algebra students. In this video, we're going to prove a formula for the distance between a point and a hyperplane. So it works for planes in R3, but it also works in the higher dimension setup. So let's first read the theorem and explain the couple of the information that I already have on the board. So if P is a point in Rn, and this is the equation of a hyperplane, so we've seen this in class, then the distance from a point P to the hyperplane is given by this formula. Well, obviously the n here is the normal vector of the plane, the one that has all the coefficients. So I'll just frame this formula because that being said, you don't need it, right? Because if you remember how to properly set it up, you will never need to use that formula explicitly. You can just do the problem from scratch, like from the geometric interpretation. Okay. And before we start the proof, I want to say that okay, so the proof is going to rely on this construction, but let's talk about it a little bit later. I want to talk about this. Okay, so the proof relies on the fact that n dot x0 is equal to b. Okay, and let's highlight that. So how do you figure that out? It is, well, x0 is a point on the plane. Okay, so let's actually write this, where x naught is a point on the hyperplane. Okay, and how do you figure it out? Well, okay, so this is the origin, by the way. Okay, so like this point right here is the origin. So you go from the origin to the plane. So you have like a vector x naught, and any vector that is on the plane, you can subtract the vector x naught from it, and you will get a vector that's entirely contained in the plane. Okay, and by the definition of the normal vector, then the dot product of this vector with the plane with the vector x minus x naught must be equal to 0. Okay, and so here, so this is the normal vector times this vector over here, which we set equal to 0, and we know that the dot product is distributive. So we can distribute the dot product and send this member on the other side. And then we saw in class that the normal vector to a plane is simply the coefficients, okay? So that is actually not new. Okay, so here I'm using the result that the normal vector is really one that have the coefficients like this. Okay, and then whenever you dot product n with just x, you'll get like your x1 to xn. But then as you dot product n with x0, since you have this member on this side, well, n dot x0 will give you your b. Okay? So, okay, now that we write this down, let's do the actual proof, but I will erase this drawing, okay? And now I will explain this one. So this is the setup that we have seen in class. If you want to find the distance between a point and a plane, so by the way, the normal vector is not like this. So the normal vector might be actually like this. And then the distance would be something like this. Okay. So the idea is that this black vector over here will be the projection. Okay, so this is the projection of Q on the normal vector. Okay, so this is what this black vector is. And that's what we want to calculate. So step number 1, we have to calculate the vector Q. Okay, so vector Q is equal to, well, this is simple. It's going to be the vector P minus the vector x naught, okay, as written in this diagram. And then step number 2, you project it, right? So you will get the black vector, so projection of n on Q. And then what does this give? Well, it's going to give you Q dot n over n squared times the vector n, right? This is the formula for the projection. And from there, let's actually continue our calculation. Now, the vector Q, I remind you, is P minus x naught. So in other words, like you dot product this with n over n squared, and then multiplied with n. And now finally, what do you have here? Well, you dot product n with p. So there you go. You have like n dot product with p minus n dot product with x naught. So I'm using both commutativity and distributivity kind of at the same time. Then over n squared times n, which finally, because of what we wrote earlier, right, this we knew it's equal to b, okay? So we finally get n dot p minus b divided by n squared, okay, times n. Now, step number 3, the distance, so d, will obviously be the norm of this projection vector. So norm of the projection of Q on n. So in other words, we take this formula and put it inside of a norm. So it's like n dot p minus b over the norm of n squared times n. And now what you need to remember is that all the fraction is just a number. So we can just put it in absolute value. But absolute value on the norm of n squared is not necessary. So we're actually just going to absolute value the top. Okay, so this must be in absolute value. Then we divide by the norm of n squared. And then we take the norm of n, which after dividing gives us the result. Okay, so here I will I will skip the simplification because it will force me to erase part of the board. But as you can see, when you simplify this with this, you get exactly that formula. All right, I hope this was helpful. See you either in class or in the next video.